Today we're going to continue our review on manifolds. So we'll recall the important notions of immersions, embeddings, and submanifolds. So let's start defining the derivative. So if we have n and n smooth manifolds and a map from x to y, which is smooth, then its derivative or linearization at a point P is the linear map dfp that goes from the tangent space. Sorry, I meant to write m and n here. That goes from the tangent space of m at P to the tangent space of n at the point f of P. So if, let me draw. So if here's my manifold M, and here's my manifold N, P, and f of P, then we can look at the tangent spaces, and the derivative is going to be a linear map that will take this tangent space to this tangent space. Okay, let me just remove the lines. I think it'll be easier to see. Okay, and how do we define it? Well, you define it, it's very, if you think of tangent spaces as the space of derivations, then it's very straightforward, very canonical. You just define the derivative, apply to the vector v, eating a function on n to be basically v eating the composition of g with f. So this is very straightforward. But if you want, you can write it in charts. So in a chart, the derivative has the expression of the derivative matrix. So in a chart, you can basically write that this guy applied to d dxi p will be sort of df dxj, no, dfj, let me write it like this, sorry, dfp applied to d dxi will be df dxi j ddxj, and here take the sum over j, dd maybe y j. Okay, and by this fj here, you really should think of the composition of f with the charts in n and m, and then you look at the jth coordinate of f. Okay, so when you look in the charts in m and n, f will be a function from Rm to Rn, or for a subset of Rm to a subset of Rn. And then it's just, this is just the expression for the matrix, the derivative, the matrix, the matrix of derivatives. Okay, so this is just an intrinsic way to talk about derivatives from Rn to Rn. Okay, so now let's recall this definition. So when we have a smooth map, it's said to be an immersion if DFP is injective. And in this case, we say that we usually write it like this: M injects into N. That's the usual notation. And then it's a submersion if the derivative is surjective, and I'm actually using capital D. Sometimes people use lowercase d. And sometimes people use F sharp, which is called the push forward. But anyway, and here, usually people write like this when it's a submersion. Sometimes this means a surjective submersion, but anyway. And then I guess the most important one is an embedding. So an embedding is an immersion which is also a homeomorphism onto its image. So in other words, it's an immersion and there is a continuous inverse. And in this case, we write it like this: M embeds into N. Okay, so this, let me just write down what I said. So this condition here, that there is a continuous inverse, is the same as saying that F is a homeomorphism onto its image. Okay, and it's not very hard to see if you actually have this homeomorphism onto its image, then you have a diffeomorphism onto its image if you assume it's an immersion. Okay, so some examples, I want to just draw some examples. Well, an immersion, you can think of like immersed curves. I don't know, something like this. So you think of, so when I write this, I really mean this is the image of an S1 into R2. And you can parameterize this curve so that the derivative is always non-zero. So let me write it again. So basically you have a function from S1 to R2, and the image of this function, say something like this, and you can do this in such a way that the derivative of this f is always non-zero, which means you travel along this curve and you never stop. And this is an immersion because the derivative is non-zero, so it's in particular it's injective, but it look like it it's not an embedding because the image is not homeomorphic to the domain. In particular, we have it's not injective. So an embedding has to be injective on top of being an immersion. Okay, so an embedding implies that it's also injective. Okay, so now we can draw something kind of funny, which is we can draw a curve which is an injective immersion, but still not an embedding. So it's the following thing. So you take an interval and you map it into a curve that goes like this. So here you see that the image, this is an open interval, and so we wrap it like this, and then all the way here. And this is interesting because this function is injective, and we can it's an immersion too. We can parameterize it so that the derivative is never zero, but it's not an embedding because when you look at this point here, if you try to map this over here, this is not going to be a diffeomorphism, even a homeomorphism. Okay, because the topology here is different from the topology of, so this point here will have only one preimage, say, I don't know, somewhere here, but its neighborhood here is not the same, is not taken to the neighborhood of this point in this image. Okay, so this is not an embedding. Okay, and it's easy to draw pictures of embeddings, but I think I should say that you can do an interesting exercise which is that if f is a proper injective immersion, then f is an embedding. Proper just means that the preimage of a compact set is a compact. Okay, so you see that this is not satisfied here. If I take this little compact set here, this blue thing, if I take the closure of the blue thing, it's a compact set, but this pre-image here will have a piece that's not compact near the end of the interval. Okay, so that's what I wanted to say about embeddings. And well, it's a proposition that I'm not going to prove, but you can do it for yourselves, is that if you have an embedding, then the image of the embedding is naturally a manifold. So the image of this embedding inherits the structure of a manifold. Okay, so how do you do that? Well, you look at the image of the embedding, and how do you define charts? Well, you just go back to M, you use the homeomorphism back to M, and you take these charts. You take the charts in M. Okay? This kind of situation is what's called a submanifold. So what is a submanifold? A submanifold is, well, it's a subset of M, which happens to be a manifold of its own right, such that the inclusion map is an embedding. So that means, in particular, that it inherits a manifold structure from M. Okay, and you can. There are some nice local form theorems for submanifolds. You can basically say that locally, every submanifold can be written as like a subspace of. You can think of the chart on the submanifold as being just the restriction of a chart to the manifold that it fits in by a subspace. Okay, so we'll get to that in a little bit. And an observation is that sometimes when you have an immersion, people say that the image of the immersion is an immersed submanifold. So I'll just say this, but I don't think I'm going to use this very much. But sometimes people say immersed submanifold, and it's not really a submanifold. So it's even though it's an adjective in front of submanifold. Usually, when people say submanifold, they really mean an embedded submanifold, not an immersed submanifold. Okay. And another remark is that if you have a submanifold, Q a submanifold of M, then we can naturally see the tangent space of Q as a vector subspace of the tangent space to M at any point on Q. And from the derivations point of view, this is actually a calculation. But if you think about equivalence, the tangent space as equivalence classes of curves, then this is pretty obvious, because if you have a curve in Q going through P, then it's also a curve in M. And it's very easy to see that the equivalence relation is preserved. But I think it's an interesting exercise to convince yourself of this using the definition of tangent spaces as derivations. Okay, so let's talk about something that's not completely trivial. That's not just a definition. So if you have a map, we say that a point y is a regular value if for every point in its pre-image, the derivative of f is surjective. Okay? So in particular, a submersion is a map where every point is a regular value. Okay, so now it's a theorem that I'm kind of going to prove. So if the theorem is, if I have a regular value of f, then the pre-image is a submanifold. Okay. Well, the hardest part here is to see that the pre-image is actually a manifold. It's not very hard. I wrote it down. Let me actually delete it because I had promised that I would do the proofs live. So delete. Okay, so how do we prove that? So this is just an application of the inverse function theorem. So how do you do that? You have to show that. So we take an x, a point in the pre-image. And now we take charts around x and y. So I'm going to call these charts phi from u to Rm. I'm going to say m is a dimension of m, and psi from n to Rn. So my x is in u, and my y is in v. Okay? And then now I can look at f composed with phi inverse composed with psi. And that's going to be a map from some u tilde in Rm to Rn. And the point is that by the assumption, I can just assume that x goes to 0. Doesn't really matter, but anyway, we assume that the derivative of f tilde at 0 is surjective. That's the assumption of y being a regular point. Okay, and we can assume, for example, that y goes to 0. Okay, and now we use the implicit function theorem or the inverse function theorem. I mean, they're equivalent, whichever one you're more familiar with, to say that there has to exist local diffeomorphism near 0 in Rm, which I'm going to call G from u tilde to, I don't know, u tilde. Well, actually, I think I can assume, well, let's just do it like this. So this is a local diffeomorphism such that when you compose f tilde with G, this is now a map still from Rn to a subset of Rm to Rn, but I can assume that this u tilde tilde, I can write Rm as Rn times Rm minus n into Rn. And this function is actually takes z1 and z2 to z1. So that means that when this is 0, so that would be the pre-image of, that corresponds to the pre-image of y. So when I look at the pre-image of 0, that corresponds to the pre-image of y. This is actually just it's just Rm minus n intersection with u tilde tilde. So we just have the slice, the subspace Rm minus n. That's kind of what I was referring to earlier. Okay? So this basically means that this correspondence here will give you the chart. So this is a neighborhood of this guy. Well, let me write it like this. Neighborhood of x in the pre-image of y. And then the map that goes from here to here is the chart. Okay, so just looking through this, I mean, just taking the inverse of G will basically give you the chart. So actually, now if you look at F composed with phi inverse, composed with G, that will give you the parametrization, which is the inverse of the chart. No, sorry, it's the map that goes from. Okay, sorry. If you take G inverse, that will go and you restrict it to 0 times Rm minus n, and you compose with phi, yeah, there you go, on the other side, that will take a little section, a little open set, V in Rm minus n, and it maps it to a neighborhood of x in the preimage of y. So when you take the inverse of this map, you just invert this guy here, so it's just G composed with phi inverse. No, sorry, this is the inverse. Yeah, so we just phi G composed with phi. This will give you a chart. Okay. So yeah, maybe this is the kind of proof that you should write for yourself to be completely convinced. But the moral of the story is that this is just the inverse or the implicit function theorem. Okay, so now let's talk about a little bit about vector bundles. So what is a vector bundle? So if E and M are smooth manifolds, and pi is a surjective submersion, we call pi a vector bundle if I forgot to underline vector. If for every p in M, EP, which is the preimage of the point P, has the structure of a vector space. So first of all, notice that because I'm a surjective submersion, that means that every point on M is a regular value, so the preimage is a submanifold. But I want to suppose that it has the structure of a vector space. So it's more than a submanifold, it's a vector space. Yeah, great. Such that for every point in M, there exists an open neighborhood of it and a homeomorphism from the preimage of U to U times Rk. Okay? And so the first thing is this condition called a local triviality. So not only is the preimage of a point a vector space, but actually if I take there always exists a sufficiently small neighborhood such that the preimage of this neighborhood can be written as a product. So U times a given vector space. And let me draw a picture. I think now is a good time. A picture. The idea is that I have M, and over each point of M, I have a vector space, and I'm writing kind of a line like this, such that every time I have a point, I can always find a sufficiently small neighborhood so that this, the preimage over here is like a cylinder or a trivial, is just a product. So this would be U times Rk. And the point is that, if we look at all of M, you cannot in general say that this this bundle is M times Rk. This would be a trivial bundle, but you can at least locally say that. So this is a condition of local triviality. And what's the condition? The condition is that, well, when you take PV, you take the preimage by phi, and you project it by pi, then you get P. So another way of saying this is if you take pi inverse of U, this goes to U times Rk, and here you apply P, this goes to U, and here you project onto the first factor, you want this map here to commute. So applying pi here is the same as applying the homeomorphism and then projecting on the first coordinate. Okay? And then the second condition is that the structure of Rk is actually the vector space structure on pi inverse of P. Okay, so that means that this phi is a linear isomorphism on each fiber. Okay, so that's what it means to be a vector bundle. And I think I do want to have more space here. So let me move this around. Sorry, I'm still kind of learning how to teach a good class using my tablet. I hope I'll get better by the next, in the future. So actually, the first example that I think is that I should do before anything is if you just consider E to be M times Rk. So this is called the trivial bundle. And you kind of, the bundle is really the pair of E, M, and the map, but very often the map is implicit. So the trivial bundle, this is like this. The map pi is just the projection to the first coordinate. So this is what's called the trivial bundle. This is really, what this picture that I drew here shows, but locally. And the point is that a bundle in general is something that will imitate the trivial bundle locally, but globally, if you look at the whole M, then you won't necessarily have a trivial behavior like this. Okay, so maybe the second example, and maybe the first interesting example, is the tangent bundle. So last time I told you about the tangent space. So this is just the union, the disjoint union of all the tangent spaces, or it's called the tangent bundle. And the map pi is just the projection onto M. So it might be instructive to see why this is a bundle. Well, we have to first see, so the first condition is that the pre-image of every point P is a tangent, has a natural structure of a vector space. So this is just the tangent space. And we know that this has the structure of a vector space. I've said that last time, and because of derivations. And then we have to check the local triviality condition. I mean, this first condition here, well, we have to check the local triviality. And basically for each point P, we know that there is a chart around P. So we know that we have a chart that goes to, say, Rn. And I told you last time that this induces a map that goes from pi inverse of u to u times Rn. No, actually, last time I wrote a map to Rn times Rn, where you wrote the sum of vi ddxi p and goes to phi of p. So I just wrote the chart for the tangent bundle. But I mean, now we can just take the pre-image of phi on the first coordinate. And then you get a map to u times Rn. It's an even simpler map. You just p and then vi. I mean, obviously this guy is not defined on all of Rn necessarily. There's some subset here, which is the image of phi. So maybe I should write phi of u times Rn. Okay, but anyway, the point is that we have these local trivializations. They're pretty easy, and it's kind of clear when you write it like this that the first and the second conditions are satisfied. So this is a vector bundle. And then by the same argument, it's not hard to see that the cotangent bundle is also a vector bundle. Okay? So what can we do with vector bundles? We can do a lot of things. But one of the things is we can look at sections. So what's a section of a vector bundle? It's just a map that goes from M to E. So we often think of a vector bundle as something that's lying above M. And a section is a map that goes up. So it's a map that goes from M to E, such that the composition of pi and S is the identity of M. Okay, so sort of we often draw it like this. So we can think of this as what I'm going to draw here Think of it as being the section. So, and maybe think about this as being a graph of a function is a good example of a section. Okay? And the set of sections is called, is usually written like this, gamma of E. So now let's do some examples, and I think now that's where it's going to get more interesting. So the first example is, I would say, the prettiest of all, because it kind of always exists in a vector bundle. It's called the zero section. So if you have a vector bundle, you can just consider the map S that takes P to 0, which is the 0 in EP. And I think that's interesting because, you know, maybe it's kind of obvious, but it's not completely obvious in a sense, because you have to, because you know EP is a vector space, but you don't know a canonical isomorphism to Rn. So it's not very easy to actually say, you know, take an element of Rn or Rk and have that be your section. That doesn't work because you don't have a canonical isomorphism with Rn, but 0 is a canonical point. So given a vector space, its 0 is well defined. Okay, so you can always consider the zero section of a vector bundle. So the representation is just, you know, when I write it like this, the zero section really is thought of as this section here. Okay. So one thing that's interesting is that in general, it's not true that there always exists a section that is never 0. So if you want a never vanishing section, so if you want a section S such that S of P is never 0, that doesn't always exist. Okay, sometimes it does, sometimes it doesn't. If you have a trivial bundle, then it always exists. So if E is just a trivial bundle, then you can just take a section as being, you know, constant equals to whatever vector you want in Rk. Or you can write it like this, PV, where V is any chosen vector in Rk. So this is like a constant function, and you can just choose a vector that's different from 0. Okay, but if the bundle is not trivial, then it's not necessarily true that you can find such a section. Okay, we'll see examples, but anyway, now let's get into more interesting sections. So what is a section of the tangent bundle? Well, a section of the tangent bundle is a map from M to Tm such that S of P is a tangent vector at P. So this is called a vector field. So that means for every point of M, I choose a vector. Okay, and I want this map to vary smoothly. So this is called the set of vector fields. And it's usually denoted by this letter, like this. So that means, you know, I have my manifold, and for each point, I choose a vector in a way that this varies smoothly. Okay, and then now you might know that there are vector fields that there are some manifolds for which there are no non-vanishing vector fields. So I don't know if you've seen this, but we'll talk about this later in this course. But there's the Hairy-Ball theorem. Hairy-Ball theorem that says that if V is a vector field on Sn and n is even, then V always has a 0. So this is called the hairy ball theorem, because if you take S2, you can think of it as, you can think of a hairy S2, so you can put hair on all of S2, and you take your comb and you try to comb the hair, and the point is that there will always be these two, so there's always going to be at least one point, but generically 2 points where you have a 0, so you can't comb, you have something like that. So that's, we shouldn't need that, because our hair is not completely covered, our head is not completely covered in hair. So if you remove a point of the ball, of the sphere, then that's no longer true, but we often have it anyways. It's sometimes hard to comb our hairs. But anyway, that's the hairy ball theorem, and it's true in any even dimension. So you cannot find a non-vanishing vector field. Okay, so another example is the sections of the cotangent bundle, and this is what are called one-forms. So this is what's called one-form. So for each point, you have a covector field. For each point, you have a covector over that point. So that's called the covector field, or a differential one-form. And a very interesting construction, which I alluded to last time, is that if you have a smooth function on the manifold, then you get its differential, which is a one-form, which is it's a section of the cotangent bundle. Okay. Yeah, and I defined it last time for each point. So this is, I can define it again. So dfp, well, I can just actually say what it does to a vector field, and this will determine everything. So if V is a vector field on M, df of V is just V applied to F. Okay. So now I want to talk about a last kind of section, which is called a metric. So what is a metric on a vector bundle? And I think I'm going to add a page. How do I add a page? I don't know. I'm just going to take this, move it down. Sorry, I'm still trying to learn how to use this software. Okay, so what is a metric on a bundle? Well, first of all, given a bundle, we can consider its dual bundle. So what's the dual vector bundle? Well, this is just for each fiber, so you can consider its dual vector space. So, you know, E is the union, or it's actually a disjoint union, not topologically, but as a set, is a disjoint union of EP for all P in M. So you can consider the dual space of each of the EPs, and you can consider the EP dual. Okay? And now you can actually do another operation, which is you can look at symmetric forms on EP dual. So in fact, any operation that you can do, any natural operation you can do with vector spaces translates into operations on vector bundles. So you can do direct sums, you can do duals, and you can look at the symmetric product. So page template. Oh, great. So what is this? S2 of E star, S2 of E star is the union of S2 of E star P. So S2 of a vector space is just the set of symmetric two forms. Okay. Actually, sorry, it's the symmetric product. So if you take S2 of V dual, that's the symmetric two forms. So what does that mean? That means that it's the tensor well, this is the set of bilinear forms. Yeah, so S2 of E star P is a set of bilinear symmetric two forms on EP star. Okay, so something here is a map F from EP times EP to R, which is bilinear and symmetric. This is what it is. Okay? So now a metric on E is a section of this bundle which is positive definite. So, basically that means, S, a metric will be, let's call it G. So that means G of P will be a map from EP times EP to R, which is bilinear, symmetric, and positive definite. Definite. Okay? Okay. And I think a very interesting proposition and very useful. If you've taken Riemannian geometry, you've certainly seen this. Maybe many of you have not. Is that for any vector bundle, any vector bundle admits a metric. So how do you prove this? Well, we know that you can, for each point in M, you can find a neighborhood where the bundle is locally trivial. So for each P in M, can find a neighborhood where the pre-image of U is isomorphic to U times RK. Okay, so now let me move this. Sorry, I haven't learned how to do it better. Just going to move this down a little bit. Okay. So for each P, you can find a neighborhood where the bundle is trivial. So basically, I'm going to call this UP. So well, the first thing to notice is that we can easily find a metric on just this, on pi inverse of U. And that's just the standard inner product of on RK. So which is the standard inner product on RK. Okay? And then now we will use, and I'm going to call this GP. Okay? And then now you use partitions of unity. So of course, if you take UP for P in M, this is an open covering. Open covering of M. So now we can find a partition of unity psi j, j, and j subordinate to this open covering. And then now I just, so for each j, we know that the support of psi j is contained in some upj. So now you can just consider G, which is the sum of psi j times GPJ. So sort of by definition, because this is a partition of unity, this sum is going to be locally finite. So this G is well defined. And because phi is greater than or equal to 0, this is going to be positive definite. So you have to check. That G is indeed positive definite. But again, partitions of unity will tell you that if you have this local thing, then you can extend it to all of your manifolds. Okay, and I should say one more thing before moving on. How do I? Do this? Yes. I just want to say that if, well, let me say this is the end of the proof. So if E is the tangent bundle, then a metric on E is called a Riemannian metric. And so in particular, what we proved is that Riemannian metric always exists. So you can always find a way. You can always find an inner product on each tangent space in a way that varies continuously. Okay, so that's kind of the first result in Riemannian geometry. They can always find a Riemannian metric on a manifold. And I should add another remark, which is, I mean, I told you a very easy way to find one forms on a manifold. So just take any function and the differential is a one form. So it's a section of the cotangent bundle. So you might think, oh, can I also find an easy vector field, or a straightforward vector field on any manifold? And the answer is yes. There is this thing called the gradient vector field, but it will depend on the Riemannian metric. So if M is a manifold, and you fix a Riemannian metric, and you pick a function, then you can define a gradient vector field. So this is a vector field in M, and this is defined by G of the gradient vector field paired with something else is by definition df paired with that vector. Okay, so because G is positive definite, that means it's non-degenerate. So every time you pick a one form, you can always find a corresponding vector field here. Okay, so an exercise is to understand this remark. Okay, so let's talk a little bit about vector fields before we end. So as I told you, a vector field is a section of the tangent bundle. So maybe the first important theorem is that if I have a vector field and I fix a point in M, then there exists a unique curve, gamma, from some small interval around 0, such that the tangent of gamma is always the vector field at the point gamma of t, and gamma of 0 is equal to p. Okay, so if I have a vector field and I pick a point, there always exists a unique curve that goes through that point where the vector field is always tangent to this curve. Okay? So this is the Picard-Lindelöf theorem. Picard-Lindelöf. And I'm always assuming the vector field is smooth. So in particular, it's Lipschitz, locally Lipschitz. So that's why we have the uniqueness too. And so when we have that, we define gamma t of p to be basically just gamma of t, where gamma of t satisfies this equation here, this ODE. Okay, so this phi t is what's called the flow. And what's interesting, is basically now you can vary p and see what happens. So this is another result in ODE, which is the fact that this flow phi t is a smooth function of p. So in a small enough neighborhood of p, phi t is defined for sufficiently small t. So if you take a really small neighborhood of p, you can define phi t for every sufficiently small t. So there's a positive epsilon where the flow is defined for every t less than epsilon and bigger than minus epsilon, and this phi t is smooth. Moreover, phi of t plus s is a composition of phi t with phi s in their domains whenever it's defined. So the phi t is called the flow of the vector field. And in principle, it's not defined for every t, and it maybe it's hard to it's not even possible to define it globally. But I guess one of the main observations is that if your vector v has compact support, then the flow is defined for all time. So then this flow is actually a diffeomorphism of the manifold. Okay, it's first a smooth map. Maybe let me just say it in pieces. So first of all, this is a smooth map that takes M to M, And it's a diffeomorphism because you can look at phi at minus t, and phi minus t composed with phi t is the identity, and phi t composed with phi minus t is also the identity. That's why this is diffeomorphism. That's actually the easiest way to find diffeomorphisms, is to look at flows of vector fields with compact support. And of course, if your manifold is compact, then every vector field has compact support. So that's one situation where you always have global flows. Okay, so this is something that maybe you haven't seen, maybe some of you haven't seen in the manifolds class, but it's quite useful throughout geometry and topology. So I wanted to review the flow of vector field. Yeah. So you can also go back, like having flows, you can differentiate them and have vector fields. But you have to be a little careful because sometimes when you do that, the vector field will depend on time. It will be a non-homogeneous vector field. So yeah, if you're interested, you can look at the basic references for manifolds and read about that, or you can ask me about that tomorrow. Okay, so this is all that I wanted to review about the basic theory of manifolds. So tomorrow we'll discuss manifolds, we'll discuss this and any other thing that you'd like to know about manifolds, and then next week we'll start talking about transversality. Okay.